I will talk about the Relaxation Digital-to-Analog converter, which is a new concept interface for the Internet of Things. You know that the Internet of Things is a framework of connected nodes, which is playing a growing role in the market of traditional ICT products. Moreover, IoT sensor nodes are embedded systems which need to be really low cost, very low voltage, ultra low power, and matching-insensitive devices. A possible way to target these constraints is to rethink traditional analog design and interfaces so that they are mostly digital, since digital circuits are taking advantage of voltage and technology scaling more than analog ones. This is the framework where the Relaxation Digital-to-Analog converter has been designed. The IoT interface requirements are low power operation in the order of the microwatt, sample rates in the order of kilosample per second, and the medium-low resolutions for almost all the applications. The Relaxation DAC exploits the impulse response of a first-order RC network, which is driven by the stream of bits of the digital word to be converted, which does not need preprocessing. So all the bits are shifted LSB first, and after all the bits have been shifted, the three-state buffer is put in high impedance to hold the capacitor voltage value. If we evaluate the voltage across the capacitor at the end of the n periods, it has the following expression. If we now impose a particular condition on the ratio between the clock period t and the time constant tau, then it happens that at the end of the n periods, the final capacitor voltage, which is the DAC voltage, is proportional to the digital input code n, as expected from a conventional DAC. Here we can see an example on 3 bits where all the codes are converted. The features of the Relaxation DAC is that there is no need for capacitor matching, unlike for what happens to other capacitor-based DAC, like switched capacitor DAC. So the capacitance can be reduced down to the thermal noise limit, leading to high energy efficiency for conversion. Its simple structure makes it suitable to really low voltage operation, down and below 0.5 voltage. And since accuracy just depends on a single parameter to be calibrated, we just have to meet this condition to have full resolution. It has also an excellent linearity up to the Nyquist frequency, and there is no need for digital word preprocessing. An initial version of the Relaxation DAC has been implemented on 40 nanometer technology with 2 sample rate versions, 2 megasample per second and 400 sample per second. Both have been tested on 10-bit resolutions and achieve a really low energy per conversion of around 1 picojoule per conversion. Since the linearity just depends on a single parameter, we can see what is the effect of an error on the clock period on the converter linearity. If an error on clock period is present, we can see that an error step appears on the integral nonlinearity, and this error is maximum always at half swing. This error is also proportional to the relative error on clock period. So this feature can be used to perform a self-calibration, which imposes the equality between the 2 half swing voltages, so providing 1 LSB of maximum error across the whole swing. The self-calibration should thus measure the 2 half swing voltages and modify the input voltage of a VCO, for example, to tune the clock frequency. The proposed architecture is the following, which exploits 2 VCOs based on simple relaxation topologies. The first VCO is used to tune the clock frequency, while the second one is used along with a binary counter as a VCO-based ADC. Both VCOs are driven by the DAC itself by means of 2-pass gates. Well, the self-calibration begins at startup, where the input of VCO1 is 0. So VCO1 starts at its maximum frequency and enables the digital logic to work. An arbitrary calibration word, cal, is loaded and converted, and its voltage value is updated to the input of VCO1 in order to modify the clock frequency. Next step is to convert the first of the two half swing voltages. Here we can see the conversion waveform, and the final voltage is connected to the input of the second VCO in order to perform an analog to digital conversion of this voltage. This is performed by enabling the binary counter for each time T-clock ReDAC period, where T-clock ReDAC is the clock period of VCO1. At the end of the enabling period, the binary counter will store a digital word, which is the digital representation of the voltage VDAC of 2 to the n-1. The same procedure is performed for the other half swing voltage VDAC of 2 to the n-1 So its relative digital code is loaded and converted. Here we can see the conversion waveform on 5 bits. And the final voltage value is connected to the input of VCO2 to perform again an analog to digital conversion. At the end of the enabling period for the binary counter will store the digital word, which represents VDAC of 2 to the n-1. So once we have the digital representation of the two half swing voltages, the calibration word cal can be updated in order to modify the clock period so that the two half swing voltages are the same. Here, for example, we have to increase the clock period to impose the equality of the two half swing voltages. So the new calibration word is updated with the proportional value to the difference of the two digital codes. It is converted, and the voltage value converted is updated to the input of VCO1 so that to modify the clock frequency. All this procedure is repeated until the condition of equality between the two half swing code is matched. Here we can see the conversion waveforms across the capacitor at the input of the two VCOs. The input of VCO1 converges to the voltage value which satisfies the calibration condition, the quality of the two half swing voltages, while the input of VCO2 oscillates between the two half swing voltages until they are the same and the calibration is complete. Here it is shown in an animation what is the effect of the calibration on the converter integral nonlinearity. After calibration, we can see that the post-calibration static performance and dynamic performance are improved to provide 9 effective bits and less than 1 LSB on 10 bits of static nonlinearity. A different architecture has been proposed, which is suitable not to an IC implementation, but to an FPGA, mostly digital implementation. The first VCO has been replaced by a tunable clock divider, while the second VCO has been replaced by a voltage to time conversion. All the architecture has been implemented and tested on FPGA by using full digital blocks and some discrete components. Here we can recognize all the digital blocks that we've presented. And the discrete components have been mounted on a protoboard, where we can also recognize all the components which are needed. We used a FPGA board to test the DAC working, and ramp and digital synthesizer have been written in VHDL and synthesized in order to perform static and dynamic performance characterization of different sample rate versions of the DAC. The characterization has been performed by 16-bit data acquisition board. In this animation, we can see that the two half swing voltages become the same. So the calibration is complete. Then a ramp is converted to perform the static characterization of the DAC. After the ramp has been converted, different sine waves at different frequency and different amplitudes are converted in order to perform the dynamic performance characterization. So the different sample rate versions have been characterized by static and dynamic performance, both of them, and they, in the end, provide more than 12 bits of effective bits and a flat frequency behavior. So this converter has a very high linearity across the whole frequency range, up to the Nyquist frequency. The measured result will be submitted on TCAS1, so they cannot be presented here. Thank you for your attention.
Thank you, Roberto. You can your share screen. And I think that now it is time for the question and answer session concerning your presentation. Let's start with the first question. What are the possible applications of relaxation digital-to-analog converters?
We are targeting IoT systems, as I said. So systems which require really low power operation. And we are actually working on the fabrication of a DAC converter for biomedical applications.
Okay, thank you. We have another question. How much is your ReDAC sensitive to power supply noise? Did you try to implement a differential structure?
Yes. Actually, the ReDAC linearity depends also on the parasitics of the RC network, which is not actually of the first order. They can be compensated somehow. If we use a differential structure, these parasitics are actually reduced in simulations, since the parasitics of the resistor is split into and then has less effect on the impulse response of the RC network. It is also, until now, susceptible to supply voltage variation due to this is for the integrated version, since the VCO is currently susceptible to supply voltage variation. But it will be improved by modifying the clock tuning strategy in the next versions.
Thank you for your very detailed answer. Now we have other two questions. The first one is, did you take into account the role of phase noise of oscillators in the DAC process?
Yes, as I told, the phase noise is quite relevant. So in order to have a good relaxation DAC, we must have a low noise VCO.
Okay, thank you. And the last one is, which is the maximum achieved sample rate with these converters?
Until now, 2 megasample per second sample rate in the integrated version.
Okay, thank you. And what about the FPGA version? We saw
tens of kilosample per second.
Okay, thank you, Roberto.